Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, God of Sleep, will guide us through the scale of the universe. For now, imagine the night beginning very quietly. Not as a dramatic curtain opening, and not as a sudden launch into space, but as something much gentler, a room growing still, a window darkening, the ordinary world settling into its evening shape. In that room, everything seems to be the right size. A hand can reach a cup. A footstep crosses the floor. A door is only a few paces away. The distances that matter most in daily life are human distances, measured by arms, rooms, streets, and the few minutes it takes to move from one familiar place to another. But the universe does not begin at the edge of the room. It is already here. It is in the air between the window and your eyes. It is in the light from a lamp crossing that small space almost instantly. It is in the gravity holding your body to Earth. It is in the slow turning of the planet beneath you, carrying the room eastward through the dark. So we begin with the smallest version of cosmic scale. Not a galaxy, not a black hole, not the farthest glow of ancient light, but the quiet fact that distance and time are braided together everywhere. Light has a speed. Signals take time. Journeys take longer. And the farther we travel outward, the more the simple word far changes its meaning. A beam of light can cross the width of an ordinary room in far less time than the mind can notice. It can cross a city almost as if the city were not there. Even Earth itself, wide enough to hold oceans and continents and weather systems, is small to light. From one side of our planet to the other, light needs only about 4/100ths of a second. That is the first strange step. Earth feels enormous to us, and it is enormous in the language of bodies. It takes hours to fly over an ocean. It takes days to sail across one. It takes months to walk across a continent, if a person could do it steadily and safely. Yet to light, Earth is a small bead, crossed almost before the sentence can finish. The planet is about 12,700 kilometers wide. It is wide enough to hide the horizon, wide enough that the sky changes as you move across it, wide enough that one side can sleep while the other side turns through daylight. And still, in the larger language of the universe, it is our first small reference point. The scale of the universe is not just a ladder of bigger and bigger things. It is a ladder of waiting times. How long must light travel? How long must a radio message wait before it is heard? How long would a spacecraft need, moving with the speeds we actually know how to make? How long would a thought experiment take if we could travel at 1/10 the speed of light, or 1/100th, or almost the speed of light itself? Those questions will carry us outward. They will let the universe become large in a way the mind can feel, not only count. We will begin at Earth, pass the moon, and watch the first little delay appear in the space between two worlds. We will move to the sun, where daylight is already 8 minutes old when it touches the ground. We will drift past the planets, out toward the dim border of the solar wind, and into the long interval before the nearest star. Then the story will widen again. We will enter the Milky Way, not as a bright stripe in the sky, but as a 100,000 light-year home, full of stars, gas, dust, dark matter, and motion. We will turn inward toward the galactic center, where Sagittarius A star reveals itself through the orbits of stars and the shadow of a black hole. From there, the journey will grow stranger. Black holes will become engines. Quasars will shine from the centers of distant galaxies. Jets will draw lines longer than galaxies themselves. The Milky Way will become one member of a small local family, the local group, and that family will become one part of a larger flow of galaxies, clusters, superclusters, filaments, and voids. At the largest scale, the universe will no longer look like scattered lights. It will look like a web, bright nodes connected by filaments, enormous quiet regions between them, and patterns so large that even the word object begins to loosen. And finally, we will arrive at the most delicate number in the journey, the observable universe, about 93 billion light-years across, even though the universe is about 13.8 billion years old. That sounds at first like a contradiction. It is not. It is one of the most beautiful ideas in modern cosmology. The light has traveled for billions of years, but space itself has expanded while the light was on its way. The source of the oldest light we can see is not simply 13.8 billion light-years away now. It is much farther in present-day distance because the universe has grown during the journey. So the promise of this episode is simple and large. We are going to measure the universe by waiting. By the time we return to Earth, the room will still be quiet. The window will still hold the night, but the darkness outside it may feel different. Not empty, not close, not far in any ordinary sense. Instead, it may feel layered with delays, ancient light, unreachable horizons, and the slow patience of space. Stand first on Earth. Not above it yet, not looking back from orbit. Stand on it as a living surface, with weight beneath your feet and air around you. This is the scale the body understands. The planet curves away in every direction, but from the ground, the curve hides itself. The horizon pretends the world is small. Hills, buildings, trees, clouds, and the edge of the sea all teach the eye to think locally. Even the sky seems like a dome rather than an opening. But Earth is a sphere more than 12,000 kilometers across. It turns once every day, carrying the surface at different speeds depending on latitude. It holds oceans deep enough to drown mountains and mountains high enough to pierce the weather. It carries the moon, not in a literal circle drawn in the sky, but in a long gravitational dance. The moon is our first cosmic companion. It looks close because it is familiar. It changes shape through the month. It lights clouds. It pulls tides. It has been visited by human beings, which makes it feel almost local, like a distant mountain across a plain. And it is local in one sense. The moon is the nearest large world to Earth. Its average center-to-center distance is about 384,000 kilometers. On the scale of planets and stars, this is a small step. On the scale of the body, it is immense. Light crosses that distance in about 1.3 seconds. That is the first useful pause in the universe. A pulse of light leaves Earth, crosses the space between worlds, touches the moon, and arrives a little more than a second later. If that pulse reflects back, the round trip takes about 2.6 seconds. This is not only an image, it is a measurement, a Apollo astronauts left retroreflectors on the lunar surface, small arrays that can send laser light back toward Earth. Scientists can fire a laser pulse from Earth, wait for the faint return, and measure the Earth-Moon distance with astonishing precision. The Moon is far enough for the delay to be felt by instruments, but close enough for the delay to be human in length. 1 second, 2 seconds, a breath. That makes the Moon a perfect first rung. It teaches the difference between seeing and arriving. We see the Moon where it was about 1.3 seconds ago. For ordinary life, that difference means almost nothing. The Moon has not moved much in that time, but the principle is already there. Looking into space is never quite looking at now. It is looking at light that has been traveling. Human travel tells another story. Apollo missions took about 3 days to reach the Moon. 3 days for a journey light makes in just over a second. The distance is the same, but the clock changes depending on what is moving. This contrast will return again and again. Light time and travel time are not the same experience. A radio signal is not a spacecraft. A spacecraft is not a human walking, and a human walking is not a beam of light. The Moon also shows that distance is not fixed in a perfectly simple way. Its orbit is slightly elliptical, so sometimes it is closer and sometimes farther. The number we use is an average, a calm center for a changing relationship. That is true of many distances in astronomy. Planets move, stars move, galaxies move. Even space itself expands at the largest scale. For now, though, the Moon gives us a gentle first lesson. If Earth were a small globe on a table, the Moon would not be pressed against it like a decoration. It would be out in the room, separated by a surprisingly large gap. Most classroom diagrams compress this space because the real spacing is inconvenient. To show Earth and Moon at true scale, the paper must become wide and quiet. The same will happen with everything else. Each time we make the objects the right size, the distances grow almost embarrassingly large. The universe is not only made of objects, it is made of intervals. The first interval is the space between Earth and Moon, a little more than a light second wide. The same will happen with everything else. Each time we make the objects the right size, the distances grow almost embarrassingly large. The universe is not only made of objects, it is made of intervals. The first interval is the space between Earth and Moon, a little more than a light second wide. From the Moon, Earth would hang in the black sky as a bright blue-white disk. It would show weather moving across it. It would show oceans and continents. It would not rise and set in the same way the Moon does for us if you stood on the near side. It would stay in the lunar sky, turning slowly, full of color. And from that distance, all human history fits into a small, shining sphere. Every city, every forest, every night road, every sleeping person, every telescope that ever looked outward, all of it is wrapped inside that blue point. The Moon is close enough to remind us of home. It is far enough to begin the universe. From the Moon, drift outward toward the Sun. At first, the Sun does not seem like a distant object. It seems like the condition for everything nearby. It is not only a star in the sky. It is daylight, warmth, seasons, weather, photosynthesis, and the main gravitational anchor of our local system. But the sun is also a place, and it is far away. Earth orbits at 1 astronomical unit from the sun, about 150 million kilometers. That number is large enough to become slippery, so astronomy gives it a calmer name, 1 AU. The average Earth-Sun distance becomes a ruler. Mercury is inside it. Mars is outside it. Jupiter is about 5 times farther from the Sun than Earth is. Neptune is about 30 times farther. Sunlight takes about 8 minutes and 20 seconds to reach Earth. That means daylight is old when it arrives. Not old like a fossil, not old like a galaxy, but old enough to have crossed a real distance. The sunlight warming your hand left the sun more than 8 minutes earlier. If the sun could suddenly change, we would not see that change instantly. The news would travel at light speed and Earth would wait. This is one of the gentlest ways to feel cosmic scale. The sun fills the day and still requires a delay. The thing that feels most immediate in the sky is already a message from the recent past. The sun itself is enormous compared with Earth. About 100 Earths could fit across its diameter in rough terms, and about 1.3 million Earth volumes would fit inside the sun. But even that comparison must be handled softly. The sun is not an empty container. Earths do not sit inside it like marbles in a jar. It is a volume comparison, a way of saying that the star at the center of our system is vast compared with the planet that receives its light. And yet, on the next scale, the sun becomes small. Imagine shrinking the sun to a tiny printed dot, about a millimeter across. Earth becomes almost impossibly tiny, a speck too small to handle, and it would orbit roughly 11 centimeters away. Jupiter would be roughly half a meter from the dot. Neptune would be several meters away. Already the room is being used up. The planets do not fit in a neat decorative circle. They spread outward into silence. But the nearest star, Proxima Centauri, would not be on the table or across the room or even in the house. On that same scale, it would be tens of kilometers away. The dot-sun analogy is useful because it makes the failure of diagrams visible. You can shrink the sun, but the space between stars refuses to shrink politely. The solar system itself does not have a single clean edge. There is Neptune, the outermost major planet. There is the Kuiper Belt, with icy bodies and dwarf planets. There is the heliopause, where the solar wind bubble gives way to interstellar space. Far beyond that, in theory, there is the Oort cloud, a vast, distant reservoir of icy objects surrounding the sun. The heliopause is not a wall. It is a transition, a borderland in the flow of particles and magnetic fields. Voyager 1 crossed into interstellar space in 2012 after decades of travel. That achievement is enormous in human terms. A machine made on Earth left the main bubble of the sun's influence. But it did not arrive at another star. That distinction matters. Interstellar space begins long before the next star is reached. It is like stepping out of the light around your own house into the dark street, while the next house is still far beyond sight. At light speed, the far reaches of the Oort cloud would be a journey of roughly years, depending on how one defines its outer region. At spacecraft speed, even the sun's distant surroundings become a long, slow story. Voyager's crossing of the heliopause took about 35 years. Reaching the nearest star at Voyager-like speed would take tens of thousands of years. Parker's solar probe gives us another kind of speed. Near the Sun, it reaches extraordinary velocities, faster than any human-made object before it. But this is a peak speed in a tight solar orbit, not a steady engine for crossing interstellar space. It is a beautiful record, but not a starship shortcut. The solar system teaches scale through contradiction. It is small enough that light can cross its inner regions in minutes and hours. It is large enough that spacecraft journeys take years and decades. It is our local neighborhood, and it is mostly emptiness. The planets themselves are not packed tightly. They are small, moving worlds separated by dark intervals. If the Sun were a bright lamp in a huge field, the planets would be tiny, moving motes, each keeping its own path, with long distances between them. The inner planets are close to the fire. Mercury, Venus, Earth, and Mars occupy the warmer inner region, where sunlight is still strong and communication delays are counted in minutes. The outer planets are farther out, where sunlight thins and a radio signal must wait longer to return. At Jupiter, sunlight takes about 43 minutes to arrive. At Neptune, it is about 4 hours. By the time light reaches the outer solar system, the Sun has become not a blazing disk, but a brilliant distant point. And still, even at Neptune, even beyond Pluto, even at the heliopause, we are not truly among the stars. We are in the outer rooms of the Sun's house. The first great collapse of human intuition comes after this. Not when we leave Earth. Not when we pass the moon, not even when we cross the planetary realm. It comes when we ask how far it is from the Sun's system to the next star. The answer is not in minutes, not in hours, not in days. It is in years of light. After the solar system, space changes its character. The Sun no longer feels like the center of a crowded family. It becomes one star among many, and the word near becomes almost unrecognizable. Proxima Centauri, the nearest known star to the Sun, is a little more than 4 light-years away. In ordinary speech, a little more than 4 sounds small. 4 steps, 4 houses, 4 towns over. But a light year is not a year of time in the usual sense. It is distance. The distance light travels in 1 year, about 9.46 trillion kilometers. So Proxima Centauri is not a short hop away. It is the distance light covers in more than 4 years. This is the first true interstellar gulf. The Sun's light reaches Earth in about 8 minutes. It reaches Jupiter in less than an hour. It reaches Neptune in a few hours. It may take roughly years to reach the farthest imagined parts of the Oort cloud. But to reach Proxima Centauri, light itself needs more than 4 years. At Voyager-like speed, the journey would take tens of thousands of years. That is one of the great scale awakenings. We have already built machines that left the main bubble of the solar wind. We have already sent probes past all the major planets. We have photographed worlds from close range and measured the faint edges of the heliosphere. Yet the nearest star remains not a destination on a human schedule, but a landmark for imagination. Proxima is part of the Alpha Centauri system, a small red dwarf bound to a brighter pair. The brighter stars, Alpha Centauri A and B, are visible from Earth's southern sky. Proxima itself is too faint for the naked eye. That is a useful reminder. The nearest star beyond the Sun is not one of the brightest stars in our night sky. Closeness and brightness are not the same thing. A small dim star nearby can hide from unaided sight, while brilliant stars much farther away can shine prominently. The sky is not a flat ceiling of dots. It is a depth map with most of its depth hidden. If you look up on a clear night, the stars may seem pressed onto a single dark surface. Constellations encourage that illusion. They turn unrelated distances into patterns. A bright star in one corner of a constellation may be dozens of light years away. Another may be hundreds. They appear close because of direction, not because they are close in space. Astronomy gently dismantles that flatness. It tells us that the familiar sky is a projection, and that behind each point is a different distance, a different travel time, a different past. The method that first opened this depth for nearby stars is parallax. As Earth moves around the Sun, a nearby star appears to shift slightly against more distant background stars. The shift is tiny, but it is measurable. It is the same basic idea as holding up a finger and closing one eye, then the other, watching the finger move against the room. Nearby things shift more. Distant things shift less. With modern instruments, especially space observatories and astrometric surveys, this measuring becomes extraordinarily precise. Star distances stop being guesses and become a three-dimensional map. Still, the map is enormous. Consider the dot-sun scale again. The Sun, a printed point. Earth, almost invisible, orbiting around 11 centimeters away. Neptune, a few meters out. Then Proxima Centauri, tens of kilometers away. Between the Sun and Proxima, there is no dense chain of stepping stones. There is space, dust, thin gas, magnetic fields, faint wandering objects perhaps, and a darkness so wide that light takes years to cross it. This is why the nearest star can be both close and unreachable. It is close compared with the Milky Way. It is close compared with Andromeda. It is close compared with the cosmic web. But it is not close compared with bodies, rockets, or lives. If a spacecraft could travel at 1/10 the speed of light, Proxima would still be more than 40 years away in the outside frame, not counting acceleration, deceleration, engineering, or the difficulty of surviving the journey. At 1/100th the speed of light, the trip becomes centuries. At today's practical probe speeds, it becomes many thousands of years. Near light speed thought experiments are valuable, but they must remain thought experiments. Relativity does offer strange gifts. To a traveler moving very close to light speed, time can pass differently. A long journey may feel shorter aboard the ship than it does to people left behind. But that does not make the energy requirements small, or the engineering simple, or the distances less real in the outside universe. The stars ask for humility. And beyond the nearest stars, the galaxy opens. Our stellar neighborhood contains more than Proxima and Alpha Centauri. It includes red dwarfs, brown dwarfs, white dwarfs, brighter stars like Sirius, and many worlds we cannot see directly. Some nearby stars move rapidly across the sky over long periods. Barnard's star, for example, is famous for its proper motion, its slow, apparent drift across the background. But for a sleep-friendly journey, we do not need to inventory them all. We only need to feel what this neighborhood means. The sun is not alone. It is one star among hundreds of billions. Yet the spaces between neighboring stars are so large that the galaxy is both populated and nearly empty. This is a theme we will meet again at every scale. The universe can be full of objects and still mostly made of distance. The nearest stars are the first proof. Now, let the local stars soften into a larger form. From far outside, the Milky Way would look like a barred spiral galaxy, a broad disk of stars and gas, winding arms, a bright central region, and a halo extending beyond the visible shape. But we do not see it from far outside. We live inside it. We look through it. That is why the Milky Way appears to us as a pale band across the sky. We are looking along the plane of the galactic disk, through crowded star fields and lanes of dust. The band is not a cloud in Earth's atmosphere. It is the combined light of distant stars in our own galaxy, blurred by distance and hidden in places by interstellar dust. The Milky Way is about 100,000 light-years across in broad terms. That number is not a sharp boundary because galaxies do not end like painted circles. The visible disk fades. The halo extends. Dark matter reaches farther than the stars we easily see. But 100,000 light-years is a useful doorway into scale. At light speed, crossing the Milky Way would take about 100,000 years. That alone changes the mind. The distance to Proxima Centauri was a little more than 4 light-years. Now the galaxy is tens of thousands of times wider than that nearest star gap. If the nearest star was the next lighthouse across a dark sea, the Milky Way is the coastline, the continent, the weather system, the map itself. Our sun lies about 26,000 light-years from the galactic center in a smaller arm-like region often called the Orion Spur or local arm. It is not at the center. It is not at the outermost edge. It is in the galactic suburbs, a quiet enough region where a planetary system could orbit for billions of years while the galaxy turns around it. The Sun itself orbits the center of the Milky Way. It takes roughly 230 to 250 million years to complete one circuit. This is sometimes called a galactic year. A galactic year is so long that Earth has gone around the galaxy only around 18 to 20 times since it formed, depending on the exact period used. The dinosaurs lived on a different part of the Sun's galactic orbit. The continents moved, species arose and vanished, mountains wore down, and the solar system continued its long path through the disk. This is another way scale becomes time. The galaxy is not still. It rotates. Stars orbit. Gas flows. Spiral structure changes. The Milky Way is not a fixed painting. It is a moving system, but its motions are slow on human scales. The galaxy contains roughly 100 to 400 billion stars. That range is wide because counting stars from inside the galaxy is not like counting lamps in a room. Dust hides many regions. Small, faint stars are difficult to detect at long distances. We infer the population through surveys, models, and the light we can measure. And stars are only part of the story. The Milky Way also contains planets, likely in vast numbers. It contains nebulae, cold molecular clouds, hot ionized gas, white dwarfs, neutron stars, black holes, star clusters, dust lanes, and a halo of dark matter whose gravity shapes the motion of the visible galaxy. It is a layered ecosystem of matter and light. Yet even here, in a galaxy full of hundreds of billions of stars, most of the volume is empty. Stars are not packed like grains of sand. They are scattered like distant fires across a dark landscape. Galactic photographs make the Milky Way look dense because the view compresses depth into an image. In 3 dimensions, the spaces are vast. This is why galaxies can pass through one another during collisions without most stars directly hitting. Gravity reshapes the galaxies. Gas clouds collide. New star formation may ignite. Tidal tails may stretch outward. But individual stars are so small compared with the distances between them that direct stellar collisions are rare. The Milky Way's structure has several layers. There is the disk, where spiral arms hold many young stars, gas and dust. There is the central bulge and bar, a crowded inner region where older stars and dense motion gather. There is a halo of older stars and globular clusters surrounding the disk more loosely. And there is a dark matter halo, unseen directly but inferred from gravity, extending beyond the bright stellar shape. Mapping all of this from inside is a remarkable act of reconstruction. It is like trying to understand the shape of a city while standing in one neighborhood, unable to rise above it. Astronomers use radio waves to see through dust, infrared light to reveal hidden stars, parallax to measure nearby distances, standard candles to reach farther, and surveys to stitch the pieces together. The Milky Way is home, but it is not simple. It is also not the universe. For much of human history, the Milky Way band was a mystery, and even after telescopes resolved it into stars, the question remained, was this all there was? In the 20th century, observations showed that many fuzzy nebulae were actually other galaxies, far beyond our own. The Milky Way became one galaxy among many. This shift matters emotionally. The largest thing in our ancestral sky became one island in a cosmic ocean. Still, before we leave the Milky Way, we turn toward its center. Because at the center of this star city is a dark mass whose presence is known by motion. Toward the center of the Milky Way, the sky thickens. From Earth, that direction lies behind dust and gas, so visible light cannot show us the galactic core clearly. But infrared light, radio waves, X-rays, and other forms of observation can reach through the hidden regions and reveal a crowded center. There, stars move quickly around an invisible mass. Their orbits are not guesses drawn for beauty. They are measurements, watched over years. The stars near the center trace loops around something compact and heavy, something with about 4 million times the mass of the Sun. That object is Sagittarius A star, the supermassive black hole at the center of the Milky Way. The name sounds gentle because astronomy often sounds gentle. A constellation, a letter, a star symbol. But the object itself is one of the great scale contrasts in the galaxy. Millions of solar masses concentrated into a region tiny compared with the Milky Way. Sagittarius. The star is about 26,000 to 27,000 light-years away. The light and radio waves we receive from its region began traveling when human beings on Earth were living deep in prehistory. When we look toward the galactic center, we are not seeing its present moment. We are receiving news from tens of thousands of years ago. The Event Horizon Telescope gave the world an image of the shadow region around Sagittarius, a star. It is important to say this carefully. The image is not a photograph of a solid surface. A black hole has no visible surface in the ordinary sense. The bright ring comes from hot material and light bent by extreme gravity around the black hole's shadow. The black hole itself is known by absence and effect, by the motion of stars, by the behavior of gas, by the shape of light near the place where escape becomes impossible. An event horizon is not a material shell. It is a boundary in space-time. Outside it, light can still escape if it is aimed properly. Inside it, escape paths no longer lead outward. For a non-spinning black hole, the radius of that boundary scales simply with mass, roughly 3 kilometers for each solar mass. Real black holes can spin, which complicates the exact geometry, but the simple scale is useful for calm imagination. A black hole with the sun's mass would have an event horizon only a few kilometers across. Sagittarius, a star with about 4 million solar masses, has an event horizon scale of millions of kilometers. That is enormous by Earth standards, and yet it is tiny compared with the galactic center around it. This is one of the deep lessons of black holes. Mass and size do not grow in the way the everyday mind expects. A black hole can contain millions of solar masses and still occupy a volume smaller than many familiar astronomical distances. It is not large like a galaxy is large. It is compact. Messier 87 star, the black hole at the center of the galaxy. Messier 87 is much more massive, about 6.5 billion solar masses. Its event horizon scale is correspondingly larger, and its image was the first black hole shadow ever released by the Event Horizon Telescope. Even so, the same caution applies. We see the glowing environment in the shadow, not the interior. At the extreme end, some black holes are inferred to reach tens of billions of solar masses. These are often called ultramassive black holes. It is tempting to name a champion, a biggest one, a final record. But this is where a calm script should resist. The most extreme masses are often model-dependent and may change as observations improve. Better to say that some black holes appear to reach tens of billions of suns, and that even this is not the end of what we may learn. Black holes can be measured through time as well as size. Light would cross the event horizon scale of Sagittarius, a star, in less than a minute. Gas orbiting close to it can change on timescales of minutes. Around larger black holes, the same kinds of changes stretch into hours, days, or weeks. The physics grows with the mass. A bigger black hole is not simply stronger in the same way at every distance. it has a larger stage on which gravity plays. Black holes are often imagined as cosmic vacuum cleaners, but this is misleading. Far from a black hole, its gravity behaves like the gravity of any object with the same mass. If the Sun could somehow be replaced by a black hole of the same mass, Earth would not be sucked inward by magic. It would continue orbiting the same total mass, though the light and heat would be gone. The danger, the strangeness, and the beauty of a black hole come from closeness, compactness, and the horizon. At the galactic center, Sagittarius, a star does not swallow the Milky Way. It anchors a compact central region and helps shape the motion nearby. The galaxy is much larger than its central black hole. The black hole is not the whole city. It is the dark weight at the center of one district. And in other galaxies, when gas falls toward such a central black hole in great quantities, the center can become one of the brightest things in the universe. That is where black holes stop being merely dark. They become engines. A black hole does not shine from inside its horizon. This is the first quiet correction to carry into any story about quasars. The light of a quasar does not come from matter after it has crossed the event horizon. Once inside, in the classical picture, light cannot return to us. The brilliance comes from outside, gas, dust, and plasma spiraling inward, heating, compressing, colliding, and radiating before the final crossing. The black hole is dark. Its surroundings can be magnificent. A quasar is the brilliant central engine of an active galaxy, powered by matter falling toward a supermassive black hole. The infalling material forms an accretion disk, and gravitational energy becomes heat and light. In the most luminous cases, the central region can outshine the combined stars of the host galaxy. This is another scale inversion. A region much smaller than a galaxy can dominate the galaxy's light. Near the black hole, the time scales may be minutes, hours, days, or weeks, depending on the black hole's mass and the region being observed. But the effects can reach far outward. Some active galaxies launch jets, narrow beams of plasma guided by magnetic fields, moving at speeds close to the speed of light and extending for thousands, hundreds of thousands, or even more light years. The jet does not come from inside the black hole. It is launched by the environment around it, by the rotating disk, magnetic fields, and extreme plasma near the central engine. This distinction keeps the science clean. Nothing escapes from inside the horizon, but the region outside the horizon can be one of the most energetic environments in the universe. Imagine a tiny central engine, then a line drawn from it across a galaxy. The line may be visible in radio waves, optical light, or X-rays. It may end in lobes where particles slow and deposit energy. It may stretch beyond the visible disk. In some examples, a jet can be longer than the Milky Way is wide. The scale becomes almost musical, seconds and minutes near the horizon, years across the inner disk, thousands of years across the surrounding regions, hundreds of thousands of years along a jet. Quasars are also time machines in the observational sense. Many are far away, so their light has traveled for billions of years before reaching Earth. We often see quasars as they were when the universe was younger, when galaxies were growing, colliding, feeding their centers, and lighting their cores. The word quasar comes from their early mystery, when they appeared star-like, but had unusual spectra and enormous redshifts. They looked like points, but they were not nearby stars. They were distant active galactic nuclei, luminous across cosmic time. For a scale journey, quasars serve a special purpose. They connect the compact and the enormous. A black hole may have an event horizon measured in solar system-like distances for the largest cases, yet the energy released around it can illuminate a galaxy, drive winds, shape star formation, and send jets across intergalactic space. This does not mean black holes are monsters consuming everything around them. Most matter in a galaxy never falls in. It orbits. It drifts. It forms stars. It remains in the larger gravitational architecture. Feeding a black hole requires the right paths, the right loss of angular momentum, the right inflow of gas toward the center. In that sense, a quasar is not simply a black hole. It is a phase, a condition, an engine turned on by fuel. The Milky Way's central black hole is quiet by quasar standards. Sagittarius. A star is massive, but it is not currently blazing like a quasar. Our galaxy's center glows and flickers in certain wavelengths, but it does not dominate the sky with quasar brilliance. This quietness is part of our local cosmic weather. Other galaxies are more active. Some have centers so bright they can be seen across enormous distances. Some jets point partly toward us, changing how the light appears. Some active galaxies are classified in different ways depending on their orientation, emission, and jet behavior. The taxonomy can become technical, but the central image is simple enough for night narration. Matter falls inward. Gravity releases energy. The black hole remains dark. The space around it shines. And sometimes, from that bright center, the galaxy draws a line into the dark, a jet so long that light needs hundreds of thousands of years to travel from one end to the other. Black holes, quasars, and jets remind us that the universe cannot be understood only by size. A small region can matter at a large scale if it holds enough mass, energy, and motion. A compact center can sculpt a galaxy. A shadow can reveal a weight. A beam of plasma can turn a galactic nucleus into a lighthouse. Then, once we have seen the engines inside galaxies, we can leave the Milky Way itself. The next scale is not one galaxy, but a family of them. The Milky Way is not alone. Beyond its disk, halo, star clusters, satellites, and dark matter, there are other galaxies bound into the same local neighborhood. This neighborhood is called the local group. The name is modest, almost domestic. Local group. It sounds like a small meeting, and in cosmic terms it is. But its span is measured in millions of light years. The local group is dominated by two large spiral galaxies, the Milky Way and Andromeda. A third spiral, Triangulum, is also important, along with many smaller dwarf galaxies. The dwarf galaxies matter. They are not decorative extras. They are the majority by number, faint companions orbiting larger galaxies or moving through the group. Andromeda is the classic neighbor. Its light takes about 2.5 million years to reach us. When we see it in the night sky, faint and elongated under dark conditions, We are receiving light that began its journey before modern humans existed. The galaxy is nearby only in a cosmic sense. If the Milky Way is a city of stars, Andromeda is another city across a dark sea. The distance between the Milky Way and Andromeda is large compared with the size of either galaxy, but small compared with the distances to rich galaxy clusters and the wider cosmic web. Again, the word near shifts. A nearby star is 4 light-years away. A nearby large galaxy is millions of light-years away. A nearby cluster is tens of millions of light-years away. At light speed, Andromeda is a journey of millions of years. At 1/10 light speed, tens of millions. At current spacecraft speeds, the number becomes so large that it stops feeling like a trip and becomes a geological or cosmological comparison. The local group itself spans roughly 10 million light-years in broad documentary language. It is not a rigid ball with a painted boundary. It is a gravitationally related neighborhood, shaped by the mass of its members and its place in a larger flow. The Magellanic Clouds, visible from the southern hemisphere, are satellite galaxies of the Milky Way. They are close companions by galactic standards, rich in gas and star formation, and they remind us that galaxies come in many forms. Not all are grand spirals. Many are irregular, elliptical, diffuse, faint, or tidally disturbed. The local group also teaches that scale is relational. The Milky Way felt enormous when we were inside it. From the local group perspective, it becomes one major member of a small family. Later, from the perspective of clusters and superclusters, the local group will become a small piece of a much larger pattern. This recurring demotion is not a loss. It is part of the beauty of scale. Each home becomes a neighborhood when seen from farther out. Earth is home. The Earth-Moon system is a pair. The solar system is a local family. The stellar neighborhood is one patch of the galaxy. The Milky Way is one galaxy in the local group. The local group is one group among many in the nearby universe. And the pattern keeps widening. Andromeda and the Milky Way are moving toward one another under gravity and are expected to interact in the far future. This future encounter is often called a collision, but that word can sound too sharp. Galaxies are mostly space. When they interact, their stars usually do not crash into one another. Instead, gravity reshapes the disks, stretches tidal features, disturbs gas, and eventually merges the systems into a new form. The event is billions of years away. It is not an immediate drama. It is a slow gravitational future. For our journey, the more important point is that galaxies have relationships. They are not lonely islands in a perfectly still ocean. They move, gather, orbit, fall, merge, and trace the invisible scaffolding of mass around them. The local group is a quiet introduction to that larger structure. If we drift farther outward, individual galaxies begin to look less like cities and more like points in a map. Groups gather into clusters. Clusters link into superclusters. Flows reveal mass that cannot be seen directly. The landscape of galaxies begins to show ridges and basins. The universe becomes geographical. Far beyond the local group, galaxies gather in richer cities. A galaxy cluster can contain hundreds or thousands of galaxies bound together by gravity, along with hot gas and dark matter. In visible light, the galaxies dominate the view: spirals, ellipticals, small, faint members, bright central giants. But much of a cluster's ordinary matter may be in hot gas between the galaxies, glowing in X-rays. And much of the total mass is dark matter, inferred from gravity and lensing. So, a cluster is not simply a crowd of galaxies. It is a deep gravitational well. Galaxy motions help reveal the mass. Hot gas helps reveal the depth of the potential well. Gravitational lensing helps map the unseen matter by the way it bends light from objects behind the cluster. A cluster is a place where the visible and invisible universe can be weighed together. The distinction between a group and a cluster is partly scale and richness. The local group is modest. A rich cluster is far larger and denser. The Virgo cluster, for example, is a nearby major cluster in our larger cosmic region. Its light reaches us from tens of millions of years away, and it anchors part of the nearby large-scale structure. Beyond clusters are superclusters, but the language becomes more delicate. A cluster is usually a gravitationally bound system. A supercluster is a larger association of groups and clusters, often not bound as one single object. Its boundaries may depend on the method used to define it. This is where the universe starts to resist ordinary categories. In everyday life, an object has edges. A stone, a table, a house, a mountain. But at supercluster scale, a named structure may be more like a watershed. It is real as a pattern of flow, density, and relationship, but its boundary is not a wall. Laniakea is a beautiful example. It is often described as the supercluster region that includes the Milky Way, defined by the flow of galaxies. The name means immense heaven in Hawaiian, and it carries the right feeling for the scale. But scientifically, it should be described carefully, not as a single solid object, not as a bound megacluster, but as a flow-defined region, a basin of attraction in the nearby universe. The great attractor is another phrase that can mislead if spoken too dramatically. It is not a single hidden object pulling everything like a cosmic magnet. It is a gravitationally influential region, part of a broader mass distribution affecting galaxy motions. The name is powerful, but the reality is more diffuse and more interesting. At this scale, astronomers map not only where galaxies are, but how they move. The smooth expansion of the universe carries distant galaxies away from one another on average, but local gravity adds peculiar motions, deviations from the smooth flow. Those deviations reveal mass concentrations and valleys in the cosmic landscape. It is like watching leaves on a slow river and learning the shape of the riverbed from the way the leaves drift. The imagery must stay calm. The universe is not rushing in a panic. These motions unfold across millions and billions of years. A galaxy cluster is dynamic, but not frantic. Supercluster flows are vast and slow. Gravity writes in longhand writing. As we move outward, a new pattern begins to emerge. Clusters are not scattered randomly. They tend to lie along larger filaments and sheets. Between those denser regions are voids, enormous underdense spaces with far fewer galaxies. The universe at the largest observable scales is not a smooth fog. It is not a uniform spray of lights. It is a web. The next part of the journey is to see the web not as a metaphor only, but as a structure built by gravity. On the largest maps, galaxies trace a pattern like lace. There are dense nodes where clusters gather. There are filaments, long bridges of galaxies and gas connecting those nodes. There are sheet-like regions, broad surfaces in the distribution of matter. And between them are voids, enormous regions with much less matter than average. This is the cosmic web. It is not a literal web made of solid threads. It is a pattern in the distribution of matter, especially dark matter, gas, and galaxies. But the web image works because the structure is connected. The universe is not a jar of randomly shaken lights. Gravity amplified tiny early differences in density. Matter flowed toward matter. Denser places grew denser. Emptier regions gave up material to their surroundings. Over billions of years, the web emerged. Dark matter plays a central role. It does not shine, but it gravitates. Ordinary matter, the stuff that becomes stars, planets, gas, and people, falls into the gravitational scaffolding shaped largely by dark matter. Galaxies form in halos. Clusters gather at nodes. Filaments stretch between them. Voids are the other half of this architecture. A void is not absolute nothingness. It can contain dark matter, thin gas, and some galaxies. But compared with the cosmic average, it is sparse. It is a region where the great galaxy cities are fewer and farther between. This is important because the word void can sound like a hole carved out of reality. That is not right. A void is not a cavity with walls. It is an underdense region shaped by the same gravitational history that built the filaments. It is a quiet part of the map. Some voids span tens to hundreds of millions of light years, depending on how they are defined. The Boötes void is one famous example, often used in popular discussions, because it is large and relatively nearby in cosmic terms. But even there, the exact size depends on method and boundary. The clean phrasing is not the empty void, but one of the best-known giant underdense regions. Imagine living in a galaxy deep inside a large void. The night sky might contain local stars in your own galaxy, but the extragalactic sky beyond could look lonelier. Nearby bright galaxies might be rare. The large-scale universe might take longer to reveal itself. A civilization there could still discover cosmology, but perhaps with a different emotional route, beginning from a quieter cosmic neighborhood. The web and voids also shift our sense of scale from objects to relationships. A filament may be tens of millions of light years long. A void may require hundreds of millions of years for light to cross. These are not journeys for spacecraft. They are map features in space-time. At current human-made speeds, crossing a large void would take time so long that ordinary language fails. Even light, the fastest messenger, needs millions or hundreds of millions of years for such structures. That is why travel time remains useful. It keeps the scale from becoming a number without feeling. The cosmic web is visible through surveys. Astronomers measure galaxy positions and redshifts to build three-dimensional maps. They use simulations to see how structure grows from early density fluctuations. They use weak gravitational lensing to trace dark matter by how it distorts background light. They use X-ray observations to find hot gas in filaments and clusters. No single observation gives the whole web. It is assembled from many ways of seeing. And then, on the web, we begin naming large features: walls, arcs, superclusters, basins, attractors. Some are well mapped. Some are proposed. Some are debated. The desire to name the largest thing is understandable, but the universe does not always cooperate with record-keeping. At these scales, a structure may not be bound. It may not have an edge. It may depend on which objects were used as tracers and how sparse the survey is. A wall of galaxies is not a wall like stone. It is a long concentration in a map, a ridge in the cosmic landscape. So the safest wonder is not "this is the biggest." It is, the universe has recognizable patterns on scales so large that light itself takes hundreds of millions or billions of years to cross them. The web is the last large structure before the horizon. After it, we stop asking what object comes next and begin asking what we can ever see. Before we reach the observable universe as a whole, we need to pause at the oldest light. The cosmic microwave background, or CMB, is often described as the afterglow of the early universe. It is the oldest light we can observe in ordinary electromagnetic astronomy. But it is not a photograph of the Big Bang itself. In the very early universe, matter and radiation formed a hot, dense plasma. Light could not travel freely for long distances because it kept scattering from charged particles. The universe was opaque in a deep sense. Then, as space expanded and cooled, electrons and nuclei combined into neutral atoms. Light could finally travel freely. This happened roughly 380,000 years after the Big Bang. That first freely traveling light has been stretched by the expansion of the universe until it now reaches us as microwave radiation, faint and cold, coming from every direction. It is not a wall around us. It is a surface of last scattering in our past, the time when the universe became transparent. This image is subtle, and it matters for the final chapter. When we look at the CMB, we are not looking at an object sitting at the edge of space like a shell we might visit. We are looking back in time to the earliest light that can reach us from all directions. The CMB surrounds our view because every direction has a past. If we look far enough in any direction, we look back to the time when the universe was young and glowing. The farthest light is not ahead like a horizon on a road. It is behind everything in time. Astronomy always mixes distance and history. The moon is 1.3 seconds in the past. The sun is about 8 minutes in the past. Proxima Centauri is more than 4 years in the past. The center of the Milky Way is about 26,000 years in the past. Andromeda is about 2.5 million years in the past. Distant galaxies may be billions of years in the past. The CMB is the farthest ordinary light of all, from a time when the universe was only a few 100,000 years old. This brings us to a very careful distinction. Look back time versus present-day distance. Look-back time tells us how long the light has been traveling. Present-day, moving distance tells us how far away the source region is now, after expansion is taken into account. For nearby objects, the difference is usually small enough to ignore. The moon is where it was a second ago, but that hardly changes the story. The sun is where it was 8 minutes ago, and the difference matters slightly but not cosmologically. For distant galaxies and the CMB, the difference becomes essential. While light travels through the universe, space itself expands. The light moves toward us, but the distances between large-scale regions can grow during the journey. So the place that emitted ancient light may now be much farther away than the simple light travel time suggests. This is not because anything is flying through local space faster than light in the ordinary way. It is because the geometry of space is changing. General relativity allows expanding space to increase distances between far-separated regions. Locally, light still sets the speed limit. The CMB, then, is the doorway to the final scale. It tells us that the universe has an age, that light has a travel history, and that distance in cosmology is not a single simple word. The next question is the one many people naturally ask. If the universe is about 13.8 billion years old, how can the observable universe be about 93 billion light-years across? The answer is expansion. The observable universe is about 92 to 93 billion light-years across. Use about gently. The number depends on cosmological parameters and rounding, and public explanations often use 92 or 93. For a calm documentary, about 93 billion light-years across is the clean anchor. The radius is about 46 billion light-years in present-day moving distance. That means, in broad terms, the regions whose oldest light we can now receive are about 46 billion light-years away today, even though the light has been traveling for about 13.8 billion years. At first, this feels impossible. If light has had 13.8 billion years to travel, should the farthest visible light not be 13.8 billion light-years away? Only in a universe that did not expand. Our universe expands. While the light was traveling, the distance between large-scale regions grew. The light crossed space, but the space it crossed was not static. By the time the ancient light arrived here, the region that emitted it had become much farther away in present-day distance. This is the core idea, and it is worth saying several ways. The age of the universe is a time. The light travel time is a history. The present-day, moving distance is a map distance after expansion. They are related, but they are not the same number. The observable universe is not a ball with Earth at the physical center of everything. It is centered on us in the observational sense because every observer has their own observable universe, the region from which light has had time to reach them. A galaxy far away would have its own horizon, overlapping with ours, but not identical. The center is not a privileged cosmic location. It is simply the location of the observer. The edge of the observable universe is not a wall. It is not a border where space ends. It is a horizon of information. Beyond it may be more universe, perhaps vastly more, perhaps infinite, but its light has not had time to reach us, or may never reach us depending on expansion and cosmic horizons. This distinction keeps the ending peaceful rather than misleading. We are not approaching a cliff. We are approaching the limit of what light can tell us. Imagine standing in fog with a lantern. The edge of what you can see is not the edge of the world. It is the edge of your information. The ground may continue beyond the fog, but you cannot directly inspect it from where you stand. The observable universe is not exactly fog, but the image helps. Our horizon is a limit set by light, time, and expansion. The full universe may be much larger than the observable universe. Science has no direct measurement of the entire whole beyond our horizon. We can test the geometry and behavior of the observable part. We can build models. We can infer. But we cannot look outside the limit of light that can reach us. This is one of the deepest forms of humility in science. The observable universe is enormous beyond ordinary imagination, and it may still be only a small portion of all that exists. If we use the 93 billion light-year diameter as a frozen ruler, light would take 93 billion years to cross it. At 1/10 light speed, a frozen crossing would take 930 billion years. At 100th light speed, 9.3 trillion years. At Voyager-like speeds, the number becomes so huge that it is better to say, far beyond the age of the universe. But even those comparisons are only thought experiments. The real universe is not frozen. Expansion and horizons matter. Some regions we see as they were can no longer be reached or affected. Some light emitted now by very distant regions will never arrive here. The universe is not only large, it is dynamically separating in ways that change future possibility. This could sound lonely, but it does not have to. There is a quiet beauty in a horizon. A horizon gives the view its shape. It tells us where information ends for now. It does not make the unseen unreal. It does not make the visible small. It reminds us that knowledge itself has a landscape. The observable universe contains hundreds of billions, perhaps trillions of galaxies, depending on the estimate and how faint a galaxy can be counted. It contains galaxy clusters, filaments, voids, quasars, black holes, stars, planets, dust, radiation, dark matter, dark energy, and the ancient microwave glow of the early cosmos. It is already more than enough to fill wonder for a lifetime. And yet beyond its horizon there may be more. Not because we have seen it, but because nothing in the horizon means space must stop there. The edge is an edge of seeing, not an edge of being. Now let the journey turn back. Not quickly, not as if falling. Simply let the scale soften inward again. From the observable universe, the cosmic web becomes a delicate pattern. Filaments and voids become texture. Superclusters become neighborhoods in a map. Clusters become bright nodes. The local group becomes a small family. The Milky Way becomes a single galaxy. The sun becomes one star in a spiral disk. Earth becomes one planet in its light. And the room returns. The room was never separate from the universe. It was always inside it. The quiet floor, the window, the night, the breath of ordinary space around you, all of it belonged to the same cosmos as the CMB and the cosmic web. Scale can make Earth seem small, but small is not the same as unimportant. Earth is small compared with the Sun, the solar system, the Milky Way, the local group, the cosmic web, and the observable universe. Yet it is the place from which the universe has become aware of itself in human thought. It is the place where light is gathered by eyes, mirrors, detectors, and minds. The moon is still about 1.3 light seconds away. The sun is still about 8 light minutes away. Proxima Centauri is still more than 4 light years away. The Milky Way is still about 100,000 light years across. The observable universe is still about 93 billion light years across. But after the journey, these numbers may feel less like isolated facts and more like a set of distances in a single unfolding story. The moon taught us that even familiar space has delay. The sun taught us that daylight is a message from 8 minutes ago. The planets taught us that local space is mostly quiet distance. The nearest star taught us that nearby can mean years for light and millennia for machines. The Milky Way taught us that a galaxy can be full of stars and still mostly empty. The galactic center taught us that invisible mass can be known by motion. Quasars taught us that darkness can power light from outside the horizon. The local group taught us that galaxies have families. Clusters and flows taught us that the universe has geography. Voids and filaments taught us that emptiness and structure grow together. The CMB taught us that the oldest light comes from a time when the universe first became transparent. And the observable horizon taught us that seeing has a limit, but reality may not. This is the scale of the universe measured not only in distance, but in waiting. 1 second to the moon, 8 minutes to the sun, years to the nearest stars, tens of thousands of years across galactic regions, millions of years to neighbor galaxies, hundreds of millions of years across great structures, billions of years from ancient galaxies, and a present-day, observable diameter so large that it carries the history of expansion inside the number. The universe is not large in one way. It is large in layers. It is large by size, large by time, large by silence, large by all the light still traveling, large by all the light that will never arrive. And here, inside it, Earth turns. The night sky above the room is not a ceiling. It is a depth. Some of its light is fresh by cosmic standards. Some is older than humanity. Some left its source before Earth had complex life. Some began traveling before the sun existed, though that oldest ordinary glow has been stretched into microwaves we cannot see with our eyes. When we look outward, we look backward. When we measure distance, we measure history. When we reach a horizon, we learn the shape of our own view. So, the ending is not a wall. It is a return. Back to the planet whose diameter light crosses in a blink. Back to the moon, whose signal waits a little more than a second. Back to the sun, whose light has been traveling for 8 minutes. Back to the ordinary room, where distances are small enough for hands and footsteps. The universe remains enormous. But the room is not outside that enormity. It is held within it, quietly, completely, under the ancient light.